The last topic of the semester is linear regression and correlation. Section 10.2 and 10.3, we're going to do three big things, three main objectives for the section. We're going to determine whether a linear correlation exists between two variables, either yes or no, there appears to be a linear relationship. If a linear relationship does exist, then we're going to find the equation of the line that best fits the data. And then we're going to use that equation or something else, and we'll talk about the something else, so that if we're given one variable, we can predict the other. It's the same process as in algebra when you have two ordered pairs and you find the slope of the line containing the two ordered pairs, and then you find the equation of the line, and you can use that equation to predict other things. It's the same process. The only difference is in algebra, we only had two ordered pairs. We were only trying to find the line that fit those two ordered pairs. And in statistics, we may have 100 ordered pairs from our experiment. We're still answering the question, does there appear to be a linear relationship? If so, what's the equation of the line? And given some x, predict the y value for it. One of the things that was difficult yesterday, some folks just didn't know what I was talking about when I said slope of a line and equation of a line. That's why I added these two slides just to give you the two-slide review of the process in algebra. If we know that there's a linear relationship between two variables, x and y, we can find the slope of the line using the slope formula. And what that slope represents, and a lot of folks don't get this, yay, they get the number in the back of the book, they have the right answer for the slope, but they have no idea what it means. What slope tells you is how much y is increasing or decreasing for each unit change in x. Either as x goes up, y goes up, or as x goes down, or as x goes up, y goes down, one of those two scenarios. For example, if you give me two ordered pairs, 0, 6,000, and 10, 20,000, and you tell me that those two ordered pairs represent the value in dollars of some artwork X years after it was purchased, then this first ordered pair would be 0 years after it was purchased, or when it was purchased, the piece of artwork was worth $6,000. 10 years later, it's worth $20,000. Given those two ordered pairs, I can find the slope of the line using the slope formula, and that slope turns out to be 1,400. What that 1,400 means is each year, the value of the artwork is increasing $1,400 a year. And if you know that, then you can find the equation of the line. And here's something else that's different than algebra. In algebra, you needed this formula to find the slope, and you needed either slope-intercept form or point-slope form to find the equation of the line. We don't have time to go over all those formulas from algebra, but what we're going to do in statistics, the calculator is going to give us the equation of the line, so you don't have to worry about that. Once we have the slope, we could find the equation of the line, and here's where you don't have to worry about how we found the equation of the line. But once we find it, we can make a prediction like, well, what will this piece of artwork be worth in 15 years? Just put 15 in place of X and punch it on the calculator. How much will it be worth in 20 years? Just put 20 in place of X and punch it on the calculator. In statistics, though, experiments are going to give us more than 2 points. If we have 100 points, what's the probability that all 100 points are going to lie exactly on a perfectly straight line? Very unlikely, very unlikely. So we're not going to be able to find the equation of a line that fits all 100 points, but we'll find what's called the line of best fit, the line that fits the points as well as anything can fit the points. And then we will be able to use that equation or something else to answer questions like how much will the artwork be worth in 20 years, or what will the parking garage capacity of this garage be? that example didn't go anywhere exciting. But anyway, we'll use our equation to make predictions. All right, the basic concepts of correlation. A correlation is just some type of relationship between the x's and the y's. That relationship may be linear or it may be something else. Sometimes there is no apparent relationship between the variables, but the only thing we're going to have time to talk about is linear correlations, data that can be modeled pretty well by a straight line. And the first question on the quiz you just took was, what does R measure? R measures the strength of the linear relationship between two values. Last question on the quiz was, between what two integers does R always lie? What was that? -1 and +1. -1 would be a perfect correlation, a line that has a negative slope. +1 would be a perfect correlation for a line that had a positive slope. And then 0, there doesn't appear to be any correlation at all. The data points look like a shotgun blast. They're not forming any noticeable pattern. So R measures the strength of the linear relationship. It doesn't tell you anything about other relationships. You can see the relationship often by looking at a scatter plot. Wonder what just happened. When I re-uploaded that, I had all 4 of those on the same slide. I'm not sure how that happened. It's okay though. This first illustration shows a set of data with a pretty strong linear correlation. It looks like as your x gets bigger, your y's get consistently bigger. Certainly they don't fall exactly on a straight line, but I could guess where a line would be that kind of went through the middle of all of those points. And notice this R value, positive 0.851. 0.85 is pretty close to 1, and it's positive because the y's are increasing as the x's are increasing. The slope of the best fit line, I don't know what the best fit line would be, but I could tell its slope would be positive. This is an illustration of some data that fits more closely along a straight line than those points in A. There's less variation from that line. But this line also, I could tell, would have a negative slope, and the negative R value indicates that. The third illustration, that's the shotgun blast. There doesn't appear to be any identifiable correlation between the X's and Y values in this data. And then in the D part, there's a distinct pattern there. It's not a line, and I may or may not remember the word for what that pattern is in algebra. Does anybody remember what you call that shape in algebra in the D part? I see why you say that. Yes, in statistics, we'd say that's kind of bell-shaped. In algebra, though, starts with a P. Nobody remember? It's a parabola. And do you remember what kind of equation gives you a parabola? A linear equation gives you a line. What gives you a parabola? Starts with a Q. Quadratic equation. Now, you don't have to know that in here. I was just seeing who remembered, and that's cool. But here there definitely is a relationship between the X's and Y's, but it's definitely not a linear pattern. And R is closer to 0 than it is either -1 or +1. There's the formula for finding the correlation coefficient. If nothing else this semester has made you kiss your calculator, this one should, because we're going to find one button that calculates that correlation coefficient for us. In 1986, this is what I was doing in undergraduate at LSUS. Thankfully, I did have a calculator with a plus button on it. That's about all I had. Again, everything we talk about today is applicable only to linear correlations. There are correlations that aren't linear. We don't have time to cover them. Properties of the linear correlation coefficient are, make sure you understand what R measures. It measures the strength of a linear relationship. Make sure you understand that R is always going to be between -1 and +1. And the closer to either of those extremes, the stronger the linear relationship. The closer to 0 an R value is, the less of a linear relationship there is. If all values of either variable are converted to a different scale, the value of R doesn't change. Maybe I'm conducting some marketing experiment, and in the U.S., my money is measured in dollars, and in Europe, it's measured in euros. We would have different Y values in our ordered pairs because they're measured on different scales. It wouldn't affect your R value. The R value doesn't depend on your units. And the value of R is not affected by which variable you let be X and which variable you let be Y. If you reverse all your ordered pairs, you would still get the same correlation coefficient. R is very sensitive to outliers, so when we encounter those, we have to think about whether or not they're accurate or perhaps that was a fluke. Outliers can drastically affect your value of R. All right, first example. This is a chart that gives the cost of a slice of pizza and the cost of Subway fare in 6 years from 1960 to 2003. And we want to know if there seems to be a linear relationship between the cost of pizza and the cost of Subway fare. Now, what does your gut say? Should there really be any relationship between cost of a slice of pizza and cost of a Subway ticket? Not unless the pizza was being delivered on the Subway system, and then if Subway fare went up, pizza fare would go up also. I don't know if in any metropolis in the U.S. pizza's delivered via Subway, but my gut says no, there really wouldn't be a relationship between the cost of a slice of pizza and the cost of Subway fare. Hey, the other thing it could be, though, is inflation. If the inflation rate is the same for pizza and Subway fare, then they could both go up about the same amount over a period of time, but we still wouldn't be saying one was causing the other. They both depend on the inflation rate, but the cost of pizza itself does not affect the cost of Subway itself. We want to construct a scatter plot. I'm going to show you how to do that on the calculator, and just look at it and say, does there seem to be a linear relationship? And then we want to find that value of R. Let the calculator find it for us. All right. You enter your data in list 1 and list 2 the same way that we've always entered data. We've never had any other function that we had to have data in both lists, but here we do. So go ahead and put the cost of pizza in list 1 and the cost of Subway fare in list 2. When you get all 6 of those ordered pairs in, look up and let's all stay at the same place. Yes, sir. Okay. You missed the very beginning. We didn't get through this lecture in class yesterday because I ran around trying to help everybody individually with their calculator, and every time I did, the whole class would just burst into song. Not really, but they burst into something. So I'm not going to do that today. If you have any trouble with your calculator, hang around a minute after and I will help you, but I don't think I can fix individual issues with calculators in class and still get through the lecture. All right, so when you have those 6 ordered pairs, you need to set up your stat plot editor, once you get everything set just like it needs to be, you're not going to have to do this anymore unless you drop your calculator and it clears everything. To find that screen, press second and Y equals. Y equals is the very top leftmost button on your calculator. Very top row. And right above it, it says stat plot. So press second and stat plot. Now you want to make sure that your plot 1 is highlighted and turned on and all the others are turned off. So it's probably that way already. Probably you're not going to have to do anything. But if plot 1 is not turned on, then highlight it, go down to on and press enter and it'll turn stat plot or plot 1 on. Same thing if you need to turn plot 2 or plot 3 off, move the cursor over on the top line, for example, to plot 2, and then move on the second line the cursor over to off and press enter. Make sure you have plot 1 on and the others off. And then this is an illustration of the different kinds of graphs your calculator will do for you. We want this first one that looks like a scatter plot. So make sure you have that highlighted. And then you'd have to tell your calculator where you saved your X's and where you saved your Y's. I put my X's in list 1, my Y's in list 2. This bottom row doesn't really matter. That's just telling the calculator what kind of cursor you'd like to see, or no, what kind of mark you would like the points to be represented by. Would you just like dots or would you like pluses? It doesn't matter what you choose there. All right. Again, once you set up that screen, you shouldn't have to go back and redo that every problem. Go ahead and exit that. Just go to clear screen. And then to get that scatter plot, it's under the zoom menu. The zoom menu is about the third button on the very top row. 2 buttons over from Y equals, I think. And when you pull up that menu, you can either enter the number 9 or you can scroll down to see that 9 says zoom stat. And that's what we want. Just choose zoom stat, press enter, and that's what you should get. If you don't get that, then hang around 1 minute after class. I'll figure out what's going on with your calculator. The person who borrowed it last from the library may have been doing calculus on it and changed the settings somehow, but I'll figure out how to get your settings correct, and then you won't have to worry about it anymore. Does it look like there's a linear relationship between the cost of pizza and the cost of Subway fare? Those fit a straight line pretty well. Does that necessarily mean that the cost of pizza is affecting the cost of Subway fare? No. Very first day of class, we said correlation does not imply causation. Just because there appears to be a relationship between two things doesn't mean one of them is causing the other. And that's still true here. But yes, there appears to be a strong linear relationship. My gut says that when I do find R, what's it going to be close to based on this graph? +1, -1, or 0? It's going to be close to +1. I know it's not close to 0 because that graph looked like a shotgun blast. It's +1 because that line would have a positive slope. So to find that value of R, we need to do a linear regression t-test. It's in the same menu as t-test and one-prop z-test. You press stat, move your cursor over twice to tests, and scroll down to letter F. Letter F says linear regression. I think it says t-test. I think I left out a T right there. Does it say linear regression t-test? Okay. That is the screen that will find R for you. Once you've scrolled down to that and pressed enter, here are the things that you have to choose on that screen. Again, once you set this up, you shouldn't have to change it anymore. on this homework, but you need to tell the calculator where you saved your X's, where you saved your Y's. You want that frequency to always be 1. For reasons I'm not going into right this minute, for the linear regression t-test, you always want to have the not equal to highlighted. I'll tell you why in just a minute. But make sure you always have the not equal to highlighted. Scroll down to calculate, press enter. There's my results screen. If you get an error, the number one thing that would cause an error is if you don't have the same number of X's in list 1 as you have Y's in list 2. That would be something to look for. But if you have an error and you've already checked and you have the same number of X's and Y's, you just need to hang around a minute after class or come see me in my office and I can help you get your calculator straightened out. Now, actually, this is just the first screen of information that the calculator gives me as results. This T is a test statistic. That P is a p-value. You don't have to worry about what DF is. We're going to come back to A and B in a few minutes, but what I'm really interested in, scroll all the way to the bottom of the list. There's my correlation coefficient R. And I got R as approximately 0.988. Would you say that that's a strong enough R value to confirm a linear relationship? That's pretty darn close to 1, but how close is close enough? Well, it depends on the consequences of being wrong. That gets to confidence levels and significance levels. If somebody's going to die if you're wrong, then you want to be sure you're right. If somebody's just going to lose an hour of sleep, you can allow a little more wiggle room in your level of confidence. But we've got to find out a way to test that R value based on a certain significance level and either say, yes, R is strong enough for me to say there is enough evidence to support a claim of a linear relationship, or there's not really enough evidence to suggest a claim of linear relationship. I have no idea. I changed the order of a few things and then uploaded it to Momentum, and the order's not changed. I don't know why that is, but let me come back to that slide in just a minute. What I decided that I'd rather do first is this screen on a formal hypothesis test. Based on the words that I just said, we want to say there is enough evidence to support the claim of a linear relationship, or there's not enough evidence. Those words should have made you think, ooh, that sounds like a hypothesis test. The notation, N, is still number of pairs of sample data. R is our linear correlation coefficient for the sample data. And then there's something else that's I'm going to mention now, but later it's not going to be important. This looks like a P, kind of italicized P maybe, but it's actually the Greek letter rho. And rho is the linear correlation coefficient for the population. We're trying to say, yes, it looks like my sample has a strong linear relationship, so I'm going to make the prediction that my population also would have a strong linear relationship. The null hypothesis would be that rho is 0. If the population correlation coefficient is 0, well, 0 is a correlation coefficient, means there is no linear correlation. If that's our null hypothesis, then our alternate hypothesis would be that rho does not equal 0. That's like R, but for the population instead of the sample. So if it doesn't equal 0, then there is a linear correlation. If we and this not equal to in the alternate hypothesis is why we clicked the not equal to on the calculator a few minutes ago. We're always going to be doing a two-tail test for linear correlation, so you can just leave that not equal to highlighted. The calculator screen gave us R. It will also give us p-values, which some problems in the homework ask for a p-value. We're not really going to use them, but if it asks you, then look at your calculator and type in the p-value. In all of our other hypothesis tests, we use the p-value and the significance level, p and alpha. If p was less than alpha, what do we do with the null hypothesis? P is less than, p is low. We rejected the null hypothesis, and if p was high, we failed to reject the null hypothesis. Here, instead of using p-values, we're going to use critical values. And this is the only time that you'll need any of the tables in the back of the book. In the homework problems where it asks for critical values, there'll be a little icon you can click on, and that table will pop up so that you can see your critical values. We're going to compare our critical value, our test statistic R. We're going to compare R to the critical values we get from the table, and I'll show you the table in just a second. If the absolute value of R is bigger than the critical value, then we'll say there is a linear correlation. If the absolute value of R is less than the critical value, then we'll say there is no linear correlation. Now, there's something easier for me to remember than that absolute value of R, but that's the way the multiple choices are listed in the answers in the homework, so that's why I'm showing you absolute value of R. But it's easier for me to think about it like this. When we were trying to determine if z-scores were usual or unusual, what were our cutoff z-scores? -2 and +2. Anything inside that was or was not unusual? Was not unusual. Anything outside that was unusual. Similarly, for critical values, if we put our critical values on a number line and then our R value falls between those critical values, then there is no linear relationship. Your R is close to 0, and R close to 0 means no correlation. If our R values are outside those critical values, then they're closer to +1 or -1, and there is a correlation, a linear correlation. So let's talk about how to get these critical values off of the table A5, and then we'll be ready to conduct that hypothesis test. The critical values are the values that separate the likely from the unlikely. That's what critical values have always been. Our z sub alpha or our z sub alpha over 2, those critical values have separated what's likely to happen by chance from what's not likely to happen by chance. So those critical values for the correlation coefficient are the same thing. Anything outside them indicates there is a linear correlation. Anything inside them means there is no linear correlation. The only two things you have to know to use this table are your number of ordered pairs and your significance level. We're only going to use two significance levels, 0.05 and 0.01. So on that pizza Subway problem, how many ordered pairs did we have? We had 6 ordered pairs. And so for a significance level of 0.05, if I said find the critical values for that problem, you would read down to 6 ordered pairs, critical value or significance level 0.05, the critical value would be positive 0.81. But just like z-scores, a z of +2 and a z of -2, both of them are the same distance from the mean. Both of them have the same area to either end. Here, this critical value of positive 0.811, there's also a critical value of negative 0.811. I think in the homework, there's a plus or minus already typed for you, and then there's a box for you to type in that critical value. If you read it off the table and put it in the box, then you're saying the two critical values are positive 0.811 and negative 0.811. So I understand how to use that table. I understand that if R ends up between those two, the positive and negative critical values, there is no linear correlation. If it ends up outside, then there is a linear correlation. So I think we're not going to set up all the steps for a formal hypothesis test. We're just going to use the value of R that we found on our calculator a minute ago. The R is 0.988. And we're going to use the critical value for 6 ordered pairs and a significance level of 0.05. That was the value we just got off the table, 0.811. And we're going to compare the absolute value of our R to the critical value we got off the table. On this example, is the absolute value of 0.988 greater than the critical value or less than the critical value? It's greater than, positive 0.988 is greater than 0.811. And what does that mean? There is or is not enough evidence to say there's a linear relationship. If it's outside, close to positive 1 or negative 1, then there is a linear relationship. Now, I've talked about this for 35 minutes already, but here's how quick the homework problems are going to be for 10.2. You just put your ordered pairs in list 1, list 2. Use linear regression t-test to get the value of R. Use table A5 to get your critical value, and then compare them. If the absolute value of R is bigger than that critical value, there is a linear correlation. Otherwise, there is no linear correlation. All right. Let me switch gears here so I can start writing a few things on the notes. For the pizza Subway example, we said the absolute value of R was greater than 0.811, and so there is sufficient evidence to claim a linear relationship. So if we know that there is a linear relationship, we should be able to find the equation of a line that best fits the data. It'd be easy to do if we had just 2 ordered pairs and if we remembered point slope form from algebra. You're not going to have to remember that here because your calculator is actually going to give you the slope and the y-intercept, and that's all you need to plug in to get your equation of your line. If we only had 2 ordered pairs, go back to algebra for a second. If we only had 2 ordered pairs, let's say we're only going to use the ordered pairs for 1960 and 2003. What's the ordered pair that would represent pizza, Subway for the year 1960? If we put the cost of pizza first, it's going to be 0.15, 15 cents for pizza, 15 cents for Subway fare. In 2003, pizza's $2 and Subway fare's $2. If we only use those 2 ordered pairs, then we could find the slope of the line. And again, you're not going to have to do this in the homework, but this is just helping you understand what the calculator is giving you when it gives you the slope. If we only had these 2 ordered pairs, then and we put them into the slope formula, we would have 2 minus 0.15 over 2 minus 0.15 or 185 over 185, what's the slope of that line? 185 divided by 185 is 1. The slope of that line is 1. That means if we were only using the ordered pairs from 1960 and 2003, we would say every time pizza goes up a penny, Subway fare goes up a penny. That's what that slope 1 means. When pizza goes up 1, Subway fare goes up 1. And then what about the equation of the line? Well, we can't go back and review this from algebra and talk about point slope form. We don't have time for that. But if you just look at these two ordered pairs and notice, hey, x and y are the same thing in both of those ordered pairs, you could figure out that the equation of this line is just y equals x. Whatever x is, y is the same thing, at least for those two ordered pairs. Now, in algebra, that equation is in a form that we call slope-intercept form. And when you have an equation in that form, when the y is by itself, the coefficient of x is always your slope. And the constant on the end, if there is one, that constant is your y-intercept. Here, there is no constant on the end, so what is the y-intercept? What constant could you put on the end that wouldn't change the problem? You could put a +0 on the end, and that's your y-intercept. You don't have to remember that from algebra. You don't have to be panicking if you don't remember that from algebra, because the calculator is going to give us these two things, the slope and the y-intercept. All we have to know is put them in these two places, and there's our equation. Now, how many of the points on the table that gives the cost of pizza and the cost of Subway fare, how many of those points would lie exactly on the line y equals x? What? I see more than that. I see more than two ordered pairs where the x and the y are the same thing. How many? 4. In 1960, y equals x, in 73, in 85, and in 2003. So 4 of those ordered pairs would fit the line perfectly. What about those other 2 years, 1995 and 2002? Would they be on the same line? No, because the y doesn't equal the x. So 4 would be on the line and 2 would not. Could we find a different line that did hit all 6 points? No. I mean, it hits 4 of them, but there's no way it's going to hit the other 2. So in statistics, we're not looking for the single line that hits every point. We're looking for what's called the line of best fit, the line that fits the data as good as any line could possibly fit the data. That's going to be called the regression line. And the regression line, the regression equation, looks just like point slope form using different variables. Our little y has a y hat on it for sample y values. It's the y-intercept is written before the slope. That's no biggie. The coefficient of x is still the slope, and the constant is still the y-intercept. The calculator is going to give me the a and the b. All I have to do is round them to 3 decimal places and plop them in there, and then I'll have the equation of the line. X is called the predictor variable. You give me some value of x, and I can use it to find y, Y is called the response variable. I threw that in there just because I think on some of the homework problems it says which is the response variable, which is the predictor variable. X is predictor, Y is response. We're going to round A and B to 3 significant digits. This is called the regression equation. A picture of it, the graph of it, is called the regression line, or the line of best fit. In order to find the equation of a line, there are going to be 3 requirements we have to check. As soon as we talked about simple random sample, I said for everything else that we do the rest of the year, rest of the semester, your data is going to have to be from a simple random sample because that's the best kind of sample there is. That's true here. And then you have to look at the graph and go, yeah, it looks like a line would fit it pretty well. Pretty well subjective. It's kind of a gut level. Yeah, it looks like a line would fit it, or no, it doesn't look like a line would fit it. And then if there are outliers, they need to be investigated closely. Again, they may be accurate. They may just be this freaky fluke thing that happened once. If they're those freaky fluke things that happen once, you need to toss them out because they will significantly affect the value of R. All right, let me show you where to get that slope and y-intercept. It's the same place you got your R. When we ran linear regression t-test, we scrolled all the way down to the very bottom to get our R, and R was 0.988. Well, up at the very top, it gave us the A and the B. We just didn't talk about what they were. It even gives me the linear regression equation, so I make sure I put these numbers in the right place. The B is the slope, put it in the coefficient of X. The A is the y-intercept, put it as the constant. So for our pizza Subway data, A rounded to 3 decimal places would be 0.035. And B rounded to 3 decimal places would be 0.945. You're not even going to have to memorize this equation because your calculator's giving it to you right there. Just put 0.035 in place of A and 0.945 in place of B. And don't forget your X. That's the regression equation. And if we graphed it, its graph would be called the regression line. And we could use that equation to predict other things. We could say, so what about when pizza costs $3 a slice? What will Subway fare be then? So what if pizza costs $10 a slice? What will Subway fare be then? At the very beginning, I said there were 3 objectives. 1, determine whether or not there is a linear relationship. Well, our R being so close to +1 told us that answer was yes. The second thing we were going to do is find the equation of the line. The calculator's really going to do that for us. And the third thing we're going to do is, given a different X, make a prediction about what Y would be for that given X. All right. That is the next slide, right? Okay. Making sure my order's not getting mixed up. In that equation, what was the slope of the line? Which one of those numbers is the slope? The coefficient of X, the 0.945. Remember when we said it looks like for at least if we were only using 2 ordered pairs, it seems like every time pizza goes up a penny, Subway fare goes up a penny. That's darn close to the slope of 1. What's the y-intercept? 0.035. When we used the 2 ordered pairs for 1960 and 2003, we came up with the equation y equals x. What was the slope of that line? 1. The coefficient of x was 1. And what's the y-intercept? Since there was no constant on the end, it was 0. That was using only the first and the last ordered pair from our data, but is that pretty close to what we got when we used all the ordered pairs? Yeah, that's darn close to 1. That's darn close to 0. Is that a fluke, or should we have expected to get a slope and a y-intercept very close to this? We should have expected it, because why? There's a very strong linear relationship between the x's and the y's. For the ordered pairs, x and y were the very same thing. The other two weren't far from each other. And so, yes, I did expect that to be very similar to what I got for the regression equation. And because there is a very strong linear relationship between cost of pizza slice and cost of Subway fare. At least for that data that we had from 1960 to 2003. Now, if I was trying to make a prediction about the cost of Subway fare, let's say in 2020, would it be fair to assume that this same pattern held for 17 more years? No, things could have changed. I could predict the cost of Subway fare in that same time period, but I shouldn't predict it far away from that time period because I don't know that the same trend continued forever. That's going to be important in just a minute. We'll come back to that. All right. So you already have, everybody press zoom and number 9 again to get back to your scatter plot. Wouldn't it be cool if we could graph our regression equation, graph our regression line right on top of that scatter plot? We can. We just need to go to y equals, press your y equals button. If you have anything for anything on that screen, if you have some equations on that screen, just clear them all out one at a time. Go down to y1 and press clear, y2 and press clear until you don't have anything for any of those y's. Then go back up to y1 and type in this regression equation. 0.0346 plus 0.945. And then to type in that x, you have a button that says x and R and T and theta, I believe, are on that button. Just press it, and that's how you type in a variable. I should have. I forgot on this slide. I changed. Yeah, I just left it 4 decimal places. Being consistent with what we've done in other problems, I should have typed 0.035 right there. It's not going to be much difference, but yeah. All right. Everyone have that regression equation typed in. You see how to type your X. The top rightmost button on your calculator says graph. And unless your calculator is in some funky mode from the previous person who used it, it should put that line right on top of your scatter plot. If it is in some funky mode, hang around a minute. Come see me during my office hours. I will help you get it in all the modes set right, and it won't be a problem. You need to, if your calculator's not doing what it needs to be doing right now, then you need to see me before you start the Chapter 10 homework. That could be a problem. But sure enough, just like we said, it looks like 1, 2, 3, 4 of the points were right on that line, and 2 other points weren't far off it. So that's our line of best fit. Now, in the homework, since you can't hold your calculator up to the screen on your computer and say, here is my scatter plot, it's going to be multiple choice. You just pick A, B, or C, A, B, C, or D that looks most like the screen on your calculator. So you may have to do the scatter plot and choose A, B, C, or D, and then you'll probably have to type in the value of R. And then if it says, is there enough evidence to suggest a linear relationship, then you'll need to look at the critical values on that table and say either yes, there is, or no, there's not. Then it'll say, find the equation of the line. That's on the same calculator screen as your R, your A and your B. And then there may be a final multiple choice. So which one of these best represents the scatter plot with the regression line graphed on it? All right. We have previously determined that regression equation should fit the data pretty well. And if it does fit the data pretty well, we should be able to use it to predict, okay, what's Subway fare going to cost when pizza is $2.50? If this regression line is a good fit for the data and it can be used to make other predictions, how will I find the answer to the question, okay, what's Subway fare going to cost when pizza costs $2.50 a slice? Just put that in the place of X and punch it on your calculator. 0.0346. I'm not talking about in the graph menu. I'm just talking about on a clear screen. Type 0.03. Snap. There's another typo. I'm trying to get all my typos fixed. That's 0.0. Y'all look up and fix that on your screen. Supposed to be 0.0346, or you could just use 0.035 plus 0.945 times 250. And to the nearest penny, what is that? I didn't hear you, Gina. $2.40? Our regression equation wasn't quite the same as what we got when we only used the first and last ordered pairs. If we were only using the first and last ordered pairs, we would say, well, if pizza costs $2.50, Subway fare is going to cost $2.50 as well. Our regression equation that took in those other 2 points was a little bit different than that, but still the cost of Subway fare is pretty close to the cost of pizza. Is this likely to be an accurate prediction? Yeah, there was a very strong linear relationship. There is a very strong linear relationship. Based on that R value we found, that R value of 0.988 indicates a very strong linear relationship. All right. We've done all three objectives for that one example. We found R, said, yes, there's a strong relationship. We found the equation of the line, and we used the equation of the line to predict something else. We do need to do some more examples, but there's only one other possible twist to the puzzle. What if this had not been a good fit? What if the points were way far away from that line? If the points were way far away from that line, would you still want to use this to make your prediction? No. You know it's not a good fit. Don't use it for anything. Well, the calculator will give you an A and a B if you ask it to, whether the line actually fits the data or not. So you're going to have to be smart enough to go, well, here's my regression line, but it's not a good fit and I'm not going to use it. And then you have to figure out, so if I'm not going to use it, what do I use? That's what's on the next three slides. You can only use the regression equation when these three conditions are met. Number one, the scatter plot has to suggest that there is a linear relationship. You look at it and you go, yep, that looks pretty linear to me. Number two, that value of R lies outside the critical values, and that confirms what your gut was saying in number one. These should either both be yes or both be no. This just confirms what your eyeballs were telling you right here. And then number three, the data do not go much beyond the scope of the available sample data. When I said our pizza and Subway fare fell in the years 1960 to 2003, you wouldn't want to use that same line to make a prediction about the year 2500. It's just too far out there. So that's another thing you need to check. If any one of those three conditions are met, you can't use your regression equation. Is the calculator going to give you one anyway? Yes. Is MyMathLab going to ask for it anyway? Yes. But you're the only one who can go, oh, here it is, but I'm not going to use it. And when I can't use the regression equation, my very best prediction, and it may not be a good prediction, it's just the best I have, is going to be the mean of the sample Y's. And I added this. You might want to type this on your notes because I probably added it after you printed your notes. From a long time ago, how do we find the mean of something we have saved in a list? We press second and stat to access our list menu. We move the cursor over twice to have, it said math, didn't it? That's what's highlighted if you move your cursor over twice. And then number 7 says standard deviation. And you have to tell the calculator what list you want the standard deviation of. I don't mean standard deviation, I meant mean. Yeah, mean. Number 7 is mean. Do you want the mean of your X's or the mean of your Y's? Mean of the Y's, and in which list did you put your Y's? List 2, so make sure you tell the calculator, I want the mean of list 2. Shouldn't what? Okay. Look what Chelsea's saying here. I don't want the standard deviation. I want the mean. That's number 3, not number 7. I keep I keep trying to improve my slides, but along with improvements, there are going to be typos, and y'all are my guinea pigs on this improvement. Thanks for helping me fix it. All right. There are a lot of flowcharts in the book that I don't like. They're just so darn confusing, but I think this one's pretty good. This sums up how to tell if you have to make a prediction, and that's exactly what the problem will say. Predict the Y value. If you see the directions predict the Y value, then you have to decide, can I use my regression equation, or am I going to have to use the mean of the sample Y's? The way that you make this decision is checking these three things. Look at the scatter plot and see if it looks like a line would fit it pretty well. Look at your R value. You could put right there, if there's a linear correlation, absolute value of R is greater than the critical value, then yes, there is a linear correlation, and you're not trying to make a prediction beyond the data that you have, or very far beyond the data you have. If you answer yes to all three of these things, then take your X, plug it into the regression equation. But if you answer no to any one of those things, and really these two should always be the same, looks like a line, is a line, not is a line, but looks like a line fits it pretty well. Sure enough, a line does fit it pretty well, or not. If you can't use your regression equation, the mean of the sample Y's is what you have to use. All right, this is going so much better than yesterday. I have 3 examples. I know we can get at least 2 of them done, and that's probably enough to get you going on the homework. The homework that's actually from R.2 only asks you for R and the critical values from the table, and then either yes or no, is there a linear relationship? Because that's really all that's covered in 10.2. In 10.3, it will go on to ask questions about, okay, what's the equation of the regression line? Is it a good fit? Use it to predict something else. So I kind of broke my examples up the same way. Number 24, you have data on the price of TVs and the quality score. Maybe that's, it says from Consumer Reports. And we're trying to answer the question, does there appear to be a linear relationship between the price of a TV and its quality score from Consumer Reports? My gut says, I hope there is. I hope that the more you pay, the better you get. But as a consumer, I know that's not always true. Let's see for this data. Because it takes a few minutes, we're not, well, actually, you are going to have to type it in. Okay, go ahead and type the prices in list 1 and the scores in list 2. Jamie, go back to your Y equals menu and clear out that other equation you typed. And then do zoom 9. And let me lay your scatter plot up here for everybody to see if it looks reasonable. Yeah, okay. To get this graph that Jamie has, you'll need to clear out the other equation you typed in. Go back to Y equals and press clear. And then press zoom and choose number 9, which said stat plot, I think. Zoom number 9. If you're not getting a graph like that, come see me. Does it look like a line would fit that data very well? My gut says no, not very well at all. I could put one maybe right here that would have 3 above and 3 below, but some of the points would be pretty far from it. So, thank you, ma'am. What that tells me is the scatter plot doesn't suggest that there's a linear relationship. Let's see if our value of R confirms that. Remember where to find R? Linear regression t-test, stat, tests, and then scroll down to the letter F. Everything should already be set up correctly. You just go down to calculate, press enter. And somebody give me that R value to 3 decimal places. 0.543, is anybody second that? Is that very close to +1 or -1? Not really. But how do we determine how close is close enough? Well, if you tell me to use a significance level of 0.05, and how many data points do I have? 8. Look back at the screen where I have that table from A5. Look under the 0.05 column for significance level and the 8 ordered pairs row. I think that's right, 0.707. And really we understand that that means positive 0.707 is a critical point and negative 0.707 is another critical point. Would our R value lie between negative 0.7, positive 0.7, or outside? It would lie between. And does that mean there is a linear relationship or is not a linear? Not. That confirms what we thought when we saw the scatter plot. So would our results suggest that the more you pay, the better TV you get? Not necessarily. There doesn't appear to be a linear relationship. The problems from 10.2, that's all you have to do. Look at it, get the R value, compare it to critical values, and then say yes or no and make a conclusion. But the problems from 10.3 will go further. They will ask you for other things. It may say, predict the quality score of a rear projection television which costs $5,000. When I see those words, or that word predict, that's when I think, ooh, I better check these things on my flow chart. I better check that these are true before I use my regression equation. If I can't use my regression equation, what am I going to use? The mean of the sample Y's. Okay, so let's see if those conditions are met. Was the $5,000 within the same range of prices on our sample data? No, it's pretty far outside. Will my calculator give me a regression equation regardless? Yes, it will. If I ask, it'll give it to me, and it won't tell me, hey, don't use this. Go ahead and look on linear regression t-test and give me the value of A rounded to 3 decimal places. Three decimal places. 43.178? 48.178. Okay. Round to whatever my stat lab asks you to round to. Plus Round B to 3 decimal places for me. I'm sorry, I didn't hear you. 0.008. Don't forget your X. Otherwise, your calculator will just say, oh, I can add those two numbers. All right, the calculator gave us a regression equation. Can we use it to make this prediction? No, we've already decided it's not a good equation. We answered the questions up here. It doesn't look like a line. The R value's not close to -1 or +1. My prediction I'm trying to make is not even close to the sample data that I have. So, yay, here it is, but don't use it. And if I can't use that, what must I use instead? The mean of the sample Y's you already have those Y values saved in list 2. So say second stat, choose number 3, and tell the calculator, I want you to find me the mean of the sample Y's. Give me just to the nearest dollar. $66? No, oh, that's a credit score. I mean, a quality score, 66. I thought that was dollars for a second. It didn't make sense. But the best prediction we have, and is it likely to be a very good prediction? Not really. It's just the best we have, is that a $5,000 TV would have a quality score of 66. Now, the most common reason that people miss these predictions in 10.3 is because they get a regression equation and they use it every single time, regardless of whether it's good or not. Your calculator will give you the A and the B for that regression equation, but it can't tell you use it or don't use it. You have to figure that out based on the scatter plot and the R and whether or not you're trying to predict something that's close to your other values. If yes, then go ahead and plug the 5,000 right here. But if not, then you're going to have to use the mean of the sample Y's instead. Hey,